magical reaction. You're going to be quite impressed. In this chemical reaction, we have noodles turning into beans.
Wait, actually, no.
And beans turning back into noodles, right before your very eyes.
Holy moly.
Okay? Alright, so here's our equilibrium system, right? Noodles, beans. Okay?
I'm trying so hard.
Okay. Now, first off, let's establish a few things that equilibrium is not. Close enough. Okay. Does equilibrium, nod your head yes or no, does equilibrium mean that you have the same amount of noodles and beans? Very good. No, it does not. It could, but rarely our equilibrium is actually a 50-50. What does it mean that my system's at equilibrium? Say it louder, Zach.
The rates are equal.
The rates are equal. So every time a noodle is turning into a bean turns back into a noodle. That's why it looks like nothing is happening.
Oh my God.
But it is. You just can't see it.
Wow.
It's just happening so fast.
It's magic.
It's like Zach's hands, they move so quick, you just can't even see what's happening. Okay?
Is there a way to maximize the noodle output here?
That's actually what we're going to get to. Okay. Now, what we're talking about today is, once again, it's very conceptual, okay? We're kind of stepping, last time and the time before was more mathematical of calculating that KEQ, the actual value of it. What we're looking at today is the conceptual side of, if I stress a system at equilibrium, I mean I disrupt its balance, what does the system do to get back to a state of equilibrium? You honestly could make this lesson like an analogy to your life, because I feel like all high schoolers need to learn this, of stress management. Okay, where when stress is applied to your life, what are you going to do to get back to a state of balance? Okay, now don't say this out loud.
Cry.
And crying sometimes is a method to relieve stress, and that's okay.
Good job, Taylor.
I rub
Binge
face.
watch
High
TV.
school kids.
There's obviously better choices than others.
Ice cream. Chocolate.
Okay, so the stress, don't say it out loud. Okay, think this in your head. I'm going to apply a stress to my system. So I am the scientist, I'm the outside source. I choose, now back up, let me say one thing real quick. In my analogy, the reactants and products are in two containers. In a real chemical reaction, they'd be in a single beaker, right? Everyone understands that? Right? We're not visualized like, equilibriums aren't like jumping fountains. Right? They don't like jump.
That would be cool though.
It would be cooler, but it's not
Very
really.
fast noodles.
Okay, so I'm going to add more noodles to my system, causing it to get stressed.
Oh, it's okay, buddy.
Okay, now don't say it out loud, think in your head. What can the system do? How can the system get back to a state of equilibrium? Think in your head for a second. What can the system do to get back to a state of equilibrium? Okay, turn to your table buddy and share, and then Gavin will have you share with everybody. Ready, go.
So,
What can the system do to get back?
Make more products. Because all it has to do is just see the value where the reactant such as the noodles somehow becoming this like bean. You know, it works that way apparently, but still.
Okay, Gavin, help us out here. What can our system do to get back to a state of equilibrium?
We can apply more stress to the beans
How?
by adding more. Well, she added noodles, so like.
So, okay,
She isn't the system.
I'm
though.
not the system.
Can't trust.
You can't trust the system.
You're on the right track though, Gavin. Carly, help him out here. The system can produce more beans. So the system can take those extra noodles that I added
Genius.
and magically, play along with me here,
Wow!
They're all beans now.
Oh!
turn them into beans. Okay, now it's back to a state of equilibrium. So as we're looking at our questions today, make sure you're always answering the question in terms of what the system does to get back to equilibrium, not the original stress that was applied. Because sometimes students focus too much on what the original stress does, not how it's going to get fixed. this overall process, or this idea of shifting and balancing, is known as Chatelier or Chatelier's principle. If you speak French, you can probably say it prettier than I do. But
The chandelier.
Okay, so the whole idea of his principle is this idea of adjusting to stresses that are applied. Okay, so today we have 3 stresses we're going to talk about. We have stresses of concentration, stresses of pressure, and stresses of temperature. But the idea is always to figure out what can the system do to get back to a state of balance. Okay, so first stress, change in concentration. Now remember, change in concentration means we're going to pour more moles per liter into our container. Okay? With this particular stress, it is important to make note that pure solids, right, so it has a little s, or liquids, or I guess and liquids. Okay, so it has a little s or a little L in it. They don't change in concentration. Which means no shift of the equilibrium will occur. Because if I pour more water in, it doesn't actually change the concentration of the water. Right? It doesn't matter if I have a drop of water or a bucket of water, it's always at 100% concentration. So just be aware once again of the little subscripts in a balanced equation. Yeah, and
Wait, so I don't know if you just said this, but are there different concentrations of water?
so no, yeah, when it is pure,
Oh wait, yeah, I meant.
so no, but good question, because it is something that like seems like, well, I added more, but when you're measuring it by concentration, there's not actually any more. So.
Yeah.
Okay, now what's recognized in here is that a new equilibrium gets established as the shift occurs. So let's look at a practice problem. Okay, so here's our balanced equation. Now if it helps you, if you're a visual person, you can visualize the equations just like a scale. When I did equilibrium with Chatelier in college, this is how I did it. Is I literally would hold my hands and pretend I was a scale. Because it just helped me visualize what's going on. So if you would like to join me in the Chatelier dance, it's going to be the new biggest thing.
Is this a holding hands kind of dance?
Yeah.
No, because of COVID.
Oh.
Shoot.
No.
Hey, don't say sport.
Say sport?
Say sport. It's like,
Okay, so here's how I do it with my hands if it helps. Okay, so reactants are in this hand. I'm doing it with you, like mirroring you, right? Products are in this hand. Okay, so the stress says I'm going to add
it's a dance.
H2. Okay, H2 is a reactant. So that means the reactant side originally would get too heavy.
Alright.
Because I added more, right? You put stuff on a scale, the scale gets heavy.
Maybe it's like.
To get back to equilibrium, it needs to
Make more.
go this way.
Make the scale.
Oh!
Bro.
So I'm taking stuff from this hand and putting it over here to get back to equilibrium.
Okay, wait, so first.
So do we draw the arrow like right here?
Alright.
So our answer is that we need to shift to the products. Well, for one problem, but then if you do it for all the problems, you know, then it just
We
continues.
got the whole.
Oh.
Dance is a work in progress, I guess.
Moving.
Okay, right, it says we're gonna shift that way.
Moving NH3.
Oh my gosh.
Yay!
We need a Weird Al
Weird Al? Wait.
flip
Yes.
of the cha-cha slide.
Yes.
Ashley Chatelier.
But, oh, wait, this is gold.
Let's ride it.
Max, after school, yeah, all of us after school.
I mean, I'm gonna be in.
Go. After
I'm
test
gonna be test corrections after school.
I can't do it today.
Yeah, I can't do it today either, but maybe
We
we
should
can.
do this.
What about Friday?
When we come in for the last day of test
Is
correction,
it
we'll write
maybe
it
May
down.
8th?
Hmm?
No, that's way too far.
No, it's too late. We won't remember it at that point.
You should, because you have
Put
testing in the AP test.
Imagine we're taking the AP test. We're like, I don't remember it. And all of a sudden, we're like,
I think this song will help you.
Put
in
it,
this.
Yeah.
Wednesday.
put it in the question jar so you don't
Okay,
forget.
come back up here, everybody.
Oh, sorry.
Back to position. Okay, so now I'm choosing to remove some of my product. Okay, so here's my scale now. You gotta think like a scale. If I take something off this side, the scale goes up.
oh, so it's like the same thing.
So it needs to shift
To the front.
back that way.
And then
You always shift the side that
It's
doesn't
like
have
this.
Kind of what about
There we go, dude. We got it.
Now what's cool is this kind of goes with what you said, Gavin, of maximizing our noodle yield or something like that.
Yeah.
So in our noodle to bean reaction, if I wanted to make more noodles, what could I do to the system?
Add more beans.
If I add more beans, it would make more noodles. How else could I make more noodles?
Add
Add
more
more
noodles.
noodles.
No, then I added them.
Oh, good point.
There it is, Bryce. Say it again.
Remove noodles.
If you remove something as it's made from an equilibrium system,
Wait.
the reaction will keep making more.
So to make more, you
So you're telling me it's if we step.
We just take it out of the reaction. So it says I'm going to eat the noodles, and as I eat them, the reaction will make me more.
This would be.
Oh, yo!
Until when?
Until the beans are gone.
So what you do is you go buy like 10 pounds of beans.
And then the same deal in a container.
There you go.
Yeah, yeah, and then you just do the reaction. And you just have it kind of funnel into your mouth.
Well, no, but they're not gonna be boiling water.
Well,
Okay.
yeah, of course.
We have them go through
And then a couple
Spaghetti
beans.
sauce or just like something tasty.
Try this one with your table buddy. Come up with an answer, and then make sure you can explain one, and we'll check it first time.
Yeah.
Let me go beyond this.
I can do that.
Alright, guys, ready? The third installation of the dance right here. And it goes like this.
This one's too hot. Shift it to the reactor.
It's the dance, dude. That means left. That means left. This is right here.
You're just over here like,
My hands hurt.
Oh man!
Yay!
Looks more like a good.
Okay, sorry, 1 second.
I gotta say, we're on today.
Yeah, I know, right?
Sorry, I'm just giving them one thing to do really quickly.
Dude, my hands hurt now.
Which way are we going?
Alright, lucky
I'm
products.
just gonna drop.
Reactive.
The camera. Wait, Winston, are you doing it? Okay, the camera's on.
We should stand up and do it.
Yeah.
Do it from the Lord.
do it for the online kids.
Yeah.
Yeah.
When our goal today was not to be disruptive.
I mean, she's not here though, so it's not like.
Good points.
We're not stopping the class.
We're not stopping the class.
All right, let's perform real quick. All right,
Here
what
we
do you
go.
say?
Here we go.
Wait, but which way is products and which way is
Okay,
reactants?
wait. Let's think. Okay, products are this side.
Yeah.
Reactants are this side.
Yeah.
All right, ready. We'll start with reactants.
Okay,
Ready?
we're
I
reacting.
can't believe we're doing it. Ready? All right, products.
Oh! Dang! No! I messed it up. How did I mess it up?
Alright,
Ooh.
reactants. this song, man.
What is the-
She got it video.
She just ran away. She's like,
Wait, we're so on time. What?
You and Winston almost
She's
hit heads.
like,
I was very
yeah, she didn't even stay to watch it. She was just like, this is
so
the
on
best.
Yeah, the hand dropped that.
Yes, please are
Look at
dropping.
the mom leaves you with the babysitter, and they're like, is the babysitter okay?
Oh my God.
And they like,
I've never needed a phone more than today. Winston almost hit heads.
When I
I only met the dance 8 times. So insane. Guys, they're so good. I need this. They're so good.
Airdrop that to me.
Remember, look at us. Like, yeah, we can do this and this and this. And I was like, yeah, we can do whatever. And then the parents were only gone for like an
That's
hour.
what the song though. So like the song, you know, it's
And
Frodo.
they kept asking, they're like 30 minutes into it, they're like, we just can't wait for mom to be home.
Oh, I
I was like, you guys, she's only been gone for 30 minutes. I'm sorry, am I not bored?
We're so good.
You airdrop it out. He's
Oh yeah, you get text correction.
Wait, guys. The school one, you got it.
I don't know. How do you think I was
Where is Alviso? What the heck?
Oh, I am so proud of us.
Yeah, we're not good.
Can I seriously see the game?
Wait.
I want to
Okay.
just put forward that for the. Hey, I got this about me.
So,
I didn't get extra points. You're gonna remember this for the rest of
I know. I'm gonna remember this for the rest of my life.
No, I think they would
I
do
never
that.
actually delivered.
Yeah. And then we're like, then we should go. What are you gonna be like? When I was a kid,
So, it's
Subscribe to our YouTube channel. We do Essex pranks like this all the time.
all the time.
All the time. Here, now we're reenacting the Gettysburg Address in an English class.
Okay, no, seriously, if you're not subscribed to Mrs. Alviso, subscribe though.
Yeah, there's gonna be some great content coming.
I mean, I have to do that right now.
Are you not subscribed? I can't believe you, Winston. I thought that.
Wait, no, this one would be
Guys,
that.
what happens to Alviso?
She's sorry, man.
So it's like it's taken away. So like overall, I'd say like
We've nailed
take
it.
away one, so it's like
I propose a toast
so these
to equilibrium.
To equilibrium.
Aye. Dilly dilly. Yeah, it's actually really bad luck for toast and toast.
I have subscribed.
That's what they'll say.
I'm
Nah, it's like taboo. But you got me do it anyway. My dad did it once and the power went out.
Just like
after
a
his dad.
chemistry teacher.
Did you guys hear what happened to Texas though?
As if it was
Because of all the snow.
It's okay, we had lots of fun.
Did I
I'd have
assumed
like
you did,
KC.
so.
You did not know what happened.
I actually am really, I need to,
You're gonna have to watch the video.
want me to airdrop it?
Sorry, I just had to get them going, get our lab ready for next week. So, okay, point with your finger, keep it under your chin. If I add NH3, which way does it shift?
At NH3.
See, just do the dance, it works.
Okay, if you're pointing to the wall, have a smiley face.
Wait, but if I was both wait, that's a
I
window.
point on the window.
I have a brain.
Yeah.
I'm not sure.
Okay, now look right here, everybody. We're gonna draw these graphs later. So let me just kind of introduce you to what's going on here. So when equilibrium is achieved, concentrations are constant, right? It doesn't look like anything's changing. When we added H2, its concentration drastically spikes up because you dumped more in. But then in the process of getting reestablished, its concentration went Well, the NH3's concentration went up, and N2 went down, and then your new equilibrium gets established. So we kind of have, we're going to be drawing these graphs where we show equilibrium and then what it does, and then how does it get back to an equilibrium state again. Okay, second type of stress that we have is a change in pressure or volume. Now the first note you want to make is that pressure only affects gas molecules. So if you have an equilibrium system that's not about gases, like it's about liquid, solids, or aqueous things, pressure doesn't do anything to them. It's only about the gas. Now the whole idea, once again, is it's all about stress relief. So if you increase the pressure of a system, the system is going to adjust in a way to relieve that pressure. Now, what are ways you can relieve pressure of a chemical reaction, of a chemical system?
What if everything is solid?
True. You could open the lid. Well, technically, like, the system can't really open its lid.
What if
If it has intense pressure.
solid? That would relieve a lot of pressure.
So you're given the right track
Slow
of,
down
they're going to come together
right now.
to have less things in there. Let me look at an example now, make more sense.
We need to know
It
this.
just never stops.
Yo,
Okay, let's build a snowman. If this lesson gets done.
yo, I have a genius idea. I'm gonna put water in my mouth and I'm not going to swallow it.
That would be so helpful.
Just don't make him laugh.
It's really dark
I guess that's kind of helpful. Okay, here we go, everybody.
Just go like spit it out.
Pay attention.
Wait, I like mine.
I want to go to Snow Angel.
Okay, so here's my reaction, everybody. Okay, the stress that is being applied is I'm decreasing the volume. Now, I always link volume to pressure because I just like thinking about it in terms of pressure, but however you want to look at it. So a decrease in volume would mean that the pressure is also going up. So if you increase the pressure of a system, the system wants to relieve that pressure somehow. So to relieve the pressure, it will shift to the side with fewer moles. And I guess of gas, we should emphasize. Because if you have less things in there, the pressure will go back down. So when you're dealing with changes in pressure, what you're looking at is in the ratio of your equilibrium, how many moles of gas do you have on each side of the balanced equation? So for this particular equilibrium, we have 1 mole of gas for the reactant, and we have 2 moles of gas for the product. So if I increase the pressure, it's going to shift to the reactants because it's a 1-to-2 ratio. Vice versa, for this problem, this side of the equation has 3 moles of gas, but the product side only has 2. So an increase in pressure for this problem would cause a shift to the product side. And
So, would it affect it at all? Like, cause some things, like a mole of one thing is like, wait, that's density. Never mind.
just answer your question?
Yeah.
Okay, perfect. Any other questions about this shifting of pressure? Yeah, Carly.
Wait, so why am I decreasing the volume, like making less, increase the pressure? Is it just like making it more like tight, like in a tighter space, or like?
Yeah, because pressure is how often you collide with the walls and how hard you collide with the walls. So if I took you guys and I put you all on this half of the room with everybody else, so I decreased the volume in my classroom, and you're running around, you're going to hit the walls more because there's less space. So that's why pressure goes up. So, good question. Now what's interesting is it does not actually change the numerical value of K. Even though the individual things shift, the noodles and beans trade, the ratio of them stays constant. The only thing that will change K is temperature. If you change the temperature, then the ratio does change. But otherwise, K calculated with our rice chart stays constant. Landon.
Yeah, you spelled with an A. I mean with an
Spelled
E.
with an A.
Yeah, you spelled with
Constant.
Constantinople. Alright, water back.
Thank you.
That's still.
Okay, last stress that can be applied is temperature. So if you heat up a reaction, it can cause a stress to the equilibrium system. Now, the easy way to look at this for temperature is to look at it in terms of, is heat a reactant or is it a product? Because if you treat it like a reactant or product, then it really is just like concentration shifts. So, turn to your table buddy and remind them what it means for a reaction to be endothermic. Ready, go.
Endothermic?
Endothermic.
Endo. That means
Exo.
Oh, yeah.
So it's going in. Oh. So that means it feels cold.
Okay, so endothermic reaction, I heard it in a variety of ways. But I think we're all on the right track. That endothermic means the heat is entering the system, it's going into the reaction, which means heat can be treated like a reactant when it's endothermic. And vice versa, it can be treated like a product when it's exothermic.
Magic.
So now, once you know where the heat is, you can do it just like before with the scale of seeing which way it will shift. So for example, in this reaction here,
I felt like I was going to sneeze.
okay, so here's my chemical reaction. It tells me that the delta H is greater than 0. Now don't say it out loud. Answer in your head. Does this mean the reaction is endothermic or exothermic? Don't say it out loud. On the count of 3, you're going to show me your sign. Exo or endo. Ready? 1, 2, 3.
I don't know.
Everybody is.
You said endothermic. You are correct.
I forgot what endo.
We went like that, so that's what I doubt. I'm like,
So the way I remembered everybody is, so this means it's positive delta H, positive energy. If you have a positive bank account, that means money's going into the bank account. Endothermic, heat's going.
Yeah, if you have a negative bank account.
That means money's coming out of your bank account, right?
Uh-huh.
Okay, now what does it mean if it's endo? Heat, write this in, is like a reactant. So because it's endo, I put heat over here.
Does heat count towards the mole count?
For like pressure?
Yeah.
No. Good question though. So that means if I increase temperature and heat is like a reactant, it's going to shift the products to balance it back out.
Oh.
It's magic.
Questions on that?
Yo.
Okay, we're going to do one practice problem all together just to make sure. And then we'll do another practice problem where you have up to, I think, 8 smiley faces up for grabs.
what?
8.
No, that's still.
That's a lot of smiley.
It's gonna be thinking like, oh my god, what?
Okay, I'm drawing my graph right here. But the graph for you guys is underneath the problem. Okay? So what we're going to do is we're going to predict the stress or predict the shift and then draw on the graph the effects on the individual concentrations. Okay? So first off with these graphs, go x-axis is time as it's progressing.
Don't tell her that. Jeez.
Okay, the y-axis is concentration. Now, what you need not stress about on these graphs is the numerical values of your graph placement. These are very conceptual, and all we're looking for is just the direction of the change, meaning is the concentration going up or is the concentration going down? How much you make it go up or how much you make it go down doesn't matter here. We need a lot of data to actually know it that way, okay? So what we're going to do is I'm going to use two different colors. So we have N2O4 and we have NO2. So I'm going to have two lines, or you should have a line for everything in the reaction. So I'm going to make a line for N2O4 and a line for NO2. Now, once again, if you chose to put NO2 on top and the other one on bottom, it's fine. Because we don't really have any information to know which one is higher. We're just looking for the changes that occur. Okay? Alright, so the first stress says that we are going to add some N2O4 to the system. If I add N2O4 to the system, the first question we want to answer is which way does it shift the equilibrium?
To the right.
To the product.
N2O4 is a reactant.
So since N2 is an O4 is a reactant,
To
and
the
I
right.
add more
I
of
know, I
it,
had to do the dance for it too.
it's going to increase to the product side. Okay, so that's the first part, is answer which way it's shifting. Now for the graph, we're going to graph what's happening at time A. So the first thing that happens is N2O4 increase. So you should have a spike upward because we poured more in. So concentration went up. But then in shifting the equilibrium, what happens to the concentration of N2O4?
Goes down.
Good. So then this should gradually go down, and the products are gradually going up. Okay, let's look at time B.
Love it.
So at point B, we are removing NO2. So first thing is figure out which way is it shifting.
It goes to the right.
It's going to the products again, because N2 is a product, so if I take away product, it's going to make more to balance it out. So then on our graph, our N2O2 should spike downward because I removed it. But then in adjusting, what happens to it?
Goes
It goes back up.
Now, would it go back to the same point it was at before?
No.
You removed
Yeah, great question though, Gavin. Yeah, so you don't ever really go back to the same line you started with. But what's interesting, and once again, this is where it doesn't really matter in showing your graph, but mathematically is the ratio is actually maintained between the two. So, okay, questions on point B? Okay, point C. What's happening here? Increase the total pressure by adding N2.
Wait. Oh, that's just
the N2O4 side
Why, Taylor?
because there are less moles.
Good. So first off, N2 is not in your problem. This is just the way they're increasing the pressure, right? So when pressure goes up, you go to the side with fewer moles of gas, which would be the reactant side.
Okay.
So
So-
N2
This is a
doesn't
messed
matter.
up graph, dude.
Yeah, these are the craziest graphs you'll probably ever draw. Okay, now do I have a spike up or down at point C? No, because I didn't add or remove anything, it's just adjusting. So the adjustment is, this goes up, and this one goes down.
Science.
They could do like one of those. Oh, it just got really quiet.
It's okay. Speak your mind.
Like
Unless
they
your mind
could
is
do
blank.
those drawings. Like you could draw a picture.
I was just thinking.
Yeah.
Oh, you play like the line game with these?
Yeah, that would be so cool. Imagine you're like,
I see a
Like the
ray gun.
face and the
Does anybody
face.
else see the ray gun?
Yeah.
yes.
You see it? Yeah.
Dude, that's actually really cool.
Wait, it looks like there's a gun in Battlefront.
Yeah,
it's
it
the really
looks
short
yeah,
one.
the one that like does a ton of damage.
Yeah, but his close-up cruel's
He's definitely
power is so bad. Wait, couldn't
And
make
this
it
is
go
the
perfect.
perfect thing.
I'm not gonna erase it, but we are gonna keep going.
Dang it.
It
Ah.
looks just like
It
that.
literally looks exactly like that.
I don't know what you're talking about, but I'll take your
We'll,
word for it.
we'll pull up the picture at the end of this.
Okay, if I increase volume, that's another way of saying increase in volume also would mean decrease in pressure, which means I'm doing the opposite of what we just did on C.
So, yeah.
So I'm obviously going to shift back the other way. Right, so you see the products climb and the reactants go down.
That's so awesome.
Okay, and then for E, we are decreasing the temperature. Now, temperature you got to figure out, is it endo or exothermic is always the first question. So it tells me here that delta H is 58 kilojoules, which means
Endothermic.
endothermic. So I would put heat right here. Make a note to yourself that heat is like a reactant. So then if I decrease the heat, it's going to shift to balance out the heat.
Yes.
Yay.
Which means on our graph, let's see, that means reactants are going up again, and products
No, it just looks like,
are going
I
down.
don't even know what it looks like now.
Wait.
It's just like, it's a skate park.
Yeah. And the reflection's kind of messed up.
Okay, questions?
Wait, so it's endothermic. So
Yes.
It's on the left.
Yes.
So let's see if the dance, so you decrease the temperature. But
No,
then
no,
you go to the
careful.
right, you see?
Okay, wait, you gotta think like a scale.
Uh-huh.
If you take something off the scale, which version?
Oh, there it is. We're good. We're good.
Yeah, if you don't think like a scale, you can get it all backwards.
That was close, guys.
Okay,
I now 8 smiley faces.
turn the page,
Oh, do we have one by ourselves?
and with your table buddy, try exercise 7.9.
Okay.
Take it away from the
Yeah.
front.
So,
That means it's on
do A, B, C, D, and then graph them as well. Are they tracking the rate of the stuff or something? They're like out there again. They're trying to see how much is stoned from the last time they were out there.
Wait, I didn't see it.
Oh, no, the other side too.
All right, answer A, B, C, and D, and then make your graph.
And then we have N2 squared, and then we have H2O6.
Give you a hint to make sure you pay attention to the little details.
Wait, does that mean
so we don't need to look at
Yeah, so if you're leaning to the right, it's back to the left.
the.
Wait, but does that?
Yeah. Oh my gosh.
Wait, science
Those are
time,
really
science
good.
time.
Okay, so adding O2 to the system, so make more product, right?
Well, it would go. Yeah. So it goes this way.
Adding
Word.
N2 to make it go to the reactant. Moving H2O doesn't change anything, right?
That
So what's
means
this?
products go.
That's what
No,
I do.
this is just reactants and products. Right?
So you should actually do them all separately.
Oh.
Yeah, so you should have 4 lines.
Okay.
Are you still supposed to do water because it's a liquid?
You tell me. What would its graph look like?
Straight.
Yeah, so you could graph it here.
Wait, you're on C.
Add H2O.
You just say, do you have a knife or something? No.
Okay, wait. Adding N2 to the system. Then let's be like this.
It's going to,
I know.
so it'd be to the product. No, it'd be to the reactant.
It's a crazy story, but I'm not going to say it distract you. I'll tell you after.
Awesome.
Decrease the
Oh, yeah.
volume. Okay, wait.
Wait, so what would
What?
So it's same, but
I'm not doing that yet. I'm on B.
right?
I did
Wait.
A.
So I
This
did
is really good.
B. Okay.
Increase the volume.
I did
Well,
it.
I don't know. Because it says remove.
Wait, so what do you have for NH6? Wait, can I see your graph? So, okay, look. So just,
I haven't put these in.
Oh, I need to
I'm
write
just trying to
it.
figure out which one of these first. Oh wait, decrease volume.
Increasing the volume of
oh, you don't have to have this choice.
It's called the shock blaster.
Yeah, that's what it is.
or with
Yeah, it's called the shock blaster. It's on the jowl.
Okay,
So you have to be
so
super close.
O2 increases,
Yeah.
and then it goes down.
The pressure.
You know my favorite one now? I don't know if you got it.
Oh, yeah?
That one, like, Asian one.
this is well, I'm just
One, two,
yeah, that's good. About
Shock blaster.
We're talking about different games.
No, the first one. Yeah, I played the first one. I was like, because we have this out. But the first one is where you can do the single player stuff and you choose yours. Yeah, okay. We would always, me and my brother would always just fight out on like Hoth on those games, you know?
Hey, I beat.
Is removing the H2O removing all of it or just part of it? Part of it. Oh, okay. Because we're like, does it just stop? Like, is it just gone?
Yeah, I mean, yeah, really, you wouldn't remove all. Whenever they're talking about like a stress, so. Okay, question.
So mine went off the ground.
Yeah, first.
It looks cool. And there is more.
Okay, I'll give you one more minute and then we'll check it.
Oh my. I'm really excited to go make a story.
Is it stepping down or jumping?
It's doing a little bit of both. Because I can see over.
Like that
Oh my
liner.
gosh, y'all.
Alright, we have 20 minutes.
Perfect.
It's like a freaking tunnel.
Wait, how much longer is this?
This is it, after we check this
So
question.
like where you like draw your
No,
hand
man.
like this, and then you have to go like straight or
Wait, so
and then you like erase your like finger, so then it's just like this. That gets you. I know what you're talking about.
It kind of looks like
I got decreases volume.
So the pressure goes up and it goes to that.
Wait,
So the pressure goes up when it does that, so it goes to the side with the least amount. These are positive. So pressure goes to, so it goes to that one.
Yeah, so they don't influence like, so you don't think of it as like this has 8 mole strength, this has 7. Because really, if you shift it this way, you're only, that's just going into the liquid, which actually would decrease the pressure, not increase it. So you kind of ignore them when it comes to the
I
pressure.
would have drawn it up there. That way, you have a copy.
Okay, so here's how it will work. You get a smiley face for each one of these you got right. Okay, and then a smiley face for getting each point on the graph right. Okay, now I will give you, after we do these, I'll give you 1 minute to adjust anything on your graph if you need to. So that if you got one of these wrong, you can fix it if you feel like it needs to be
That's
fixed.
very nice of you.
I think it's important to learn from our mistakes, right?
Yeah.
Not be penalized more than once. Okay, now take your finger, and so I can kind of just get a direction you're saying it's shifting. Okay, so for A, if I add O2 to the system, point with your finger, which way will it shift? If I add O2 to the system, it will shift to the products. Questions on that? You never pointed that way. Okay, next one, if I add N2, point with your finger, which way it's going to shift? Very good. If you're pointing this way, have another smiley face. Questions on that?
I'm making
Is it
creepy smiley faces.
added? Wait, N2 is on, what's on?
N2 is a product.
So
Oh, yeah.
We're good.
I thought it was on the graph.
Oh.
Okay, if I remove water from the system, what's it gonna do?
It would go.
Product
Everyone in
oh.
the question
I said that out loud. I wasn't supposed to. Sorry.
People are like, what is going on?
No shape.
Nothing. Let's go.
Why?
Oh, it's liquid. I'm so dumb.
Yeah, it's a pure.
Oh, it's
Yeah, that's snaked in from behind.
Wherever that is, I can't see where I'm pointing.
That's snaked us, bro.
Right, so when something is a pure liquid, you can add more of it, you can do this, but it doesn't actually change its concentration amount. And if you don't change concentration, then K doesn't change, and if K doesn't change, it doesn't need to shift.
Wait, that means that's E minus.
Yeah, no, we gotta fix this.
That is right there.
Well, here it is.
Alright. We're good.
Okay.
Don't even worry about it.
So now for D, everybody ready? Point with your finger, if I decrease the volume, which way is it gonna go? So decrease in volume means, oh, I did that backwards, means increase in pressure, right?
Now I need to change all my graphs.
So if you increase the pressure, it wants to shift in the direction with fewer moles of gas.
Oh. Yes, thank goodness I switched it back.
We did it. We did it.
You only count the moles of gas.
It's switching it clean.
Okay, you have 60 seconds to change your graph before we grade those, if you want to.
You're gonna get all
My line's crossed, is that okay? I didn't plan it out.
Yeah. Once again, I care more about if it's supposed to go up, did it go up, or did it go down, so.
I mean,
My
I do
hard
more
skills are
I do. Look at mine.
Well, that's because you're using pen.
Yeah, because I forgot my pencil at home.
No, that's all.
Wait, that's
It's
okay.
4% or a little bit.
That's kind of what I did. Yeah,
So get 4.
I'm good. Mine are already.
You have so much.
Okay, I didn't really officially time you, has it been a minute?
Yeah, at least wait till it says 12.
Yeah, almost there.
We got 5 more seconds.
4,
3,
2, 1, 0. Happy New Year's.
Did you do
Okay.
the smiley face?
Check yours and let's make sure we move in the right direction. So at point A, you added O2, which means the O2 graph, the first thing it should have done is spike up.
yeah, did that.
But then in adjusting for equilibrium, it goes down.
Did that.
Both the reactants go down.
What is that?
This goes up.
Dang it. Oh, I had a feeling it was all gonna just stay the same.
Why does water not change?
You can't change its concentration.
Yeah, it's you make more, like there's probably more water in there, but in terms of molarity, it doesn't change. So make a quick adjustment if you need to.
For the rest of it.
Wait, do we have to write H2O?
Actually, no, here's something else.
Say it again, Ennis.
Do we have to write H2O?
No, so technically we don't even really need to graph H2O, because it's just going to do this. The whole time, right?
But what happens when it says H2 is removed from the system?
This one.
Yeah, does it drop?
It's just because since the graph is concentration,
Oh.
even if you remove water, the concentration doesn't drop.
It's not hard.
Does that make sense?
Yeah.
If it was measuring like grams or volume.
Concentration, that makes so much
That makes sense.
Yeah, good question.
We need to concentrate more.
Okay, ready? Okay, B, we're adding N2, so you should have a spike for N2. But then to adjust, it goes back down, and the reactants climb up.
Oh, look at him. Them go.
Alright, that's a smiley face.
Question on that one?
Yeah, Bryce, you messed up.
Okay, C has no change. So everything just stays the same.
Wow, I got that right. Wow.
Okay, and last,
what you do.
D, whatever you do, we are shifting because of pressure to the product. So which one's my product? Your black light. So product should go up. Reactant.
Yay. Alright, snow angel time.
Okay, let me say one more thing, then you go make your snow.
Okay.
Okay, any questions on that graph or the Chatelier's principle? Yeah, Zach.
If you added H2O, wouldn't that like increase the or not the temperature, the pressure to this decrease in volume?
It does get a little weird when you start thinking about like, because it would take up some of the space, and things like that. So what I'm going to say is just always assume that the amount you're changing of pure liquids and pure solids isn't significant enough to cause a shift.
It's negligible.
But yes, you are right, like in real life setting, if you were to add a ton of water, you're gonna take up space and mess up with the pressure, right? So, yeah, great thought for sure though. Okay, so for the rest of the time we have, you can make a snow angel. You can work on 7.10, which is the Chatelier shifting, or if you wanna work on any test correction stuff, you can do that as well. Okay?
Wait. I'll be so.
I feel like I should get one.
You can make a fast snow angel and still get work done.
Hey, how much time do you have?
We have 12 minutes.
12 minutes?
We won't be up in that long. Let's go. We're so productive in front of the window 3 to 6.
Yeah, we got.
Oh my
yeah.
gosh, we're going out there?
Should we film?
Yes.
Yes.
My smiling face.
Okay, students at home, this way you can enjoy what we're enjoying. Oh dear, this tripod's in my way.
The people watching us at home are like,
Are any of them going to be brave enough to make a snow angel?
I doubt it.
I know Taylor's gonna jump in.
Gavin's already doing starting. Oh, you hear something.
No! He ruined the snow!
Trust fall.
Oh, there's more than out there.
That is crazy, that wind.
It's like making it snow more than taking the snow on the ground.
Yeah, you get some major drifts in this area.
They're not even getting.
Okay, there you go, students at home. Hope you're all staying warm.